Let's talk about classless IP addressing. In a previous video, we talked about class-full IP addressing and how it may be a little bit outdated. Well, now we can talk about classless. But let's take a quick review of class-full for a second. We had Class A, which was an 8-bit subnet mask, Class B, which was 16, and Class C, which is 24. But then we came up in the 1990s with a better plan, and that was classless IP addresses. And although it looks or sounds worse, it's actually much better. So what it allows us to do is reduce wasted IP addresses. And it does that using subnetting, which we'll show here shortly. So we have 10.1.1.1 as an example. In a class full IP address, it would be a /8 subnet mask with over 16 million host addresses. But then when we use classless, basically we take that same IP address and we change it from a /8 to a /24 subnet mask, and then we end up with only 254 IP addresses. So we've saved a lot of IP addresses simply by changing the class from a Class A to a Class C. And that's one of the reasons why we were able to hang on to IP version 4 for so long before switching over to IP version 6, because we were able to save a lot of IP addresses. Various different universities and governments were handed over these Class 8 IP addresses with public addresses, and they were just sitting there not being used. And so we went in and reduced that by going to classless, and we were able to save a lot of those IP addresses and reuse them where they were needed. So 255.0.0.0 was the subnet mask, and that's now changed to what you see here, 255 3 times .0. And then we can even further change that. So 254 addresses, we can now change that to .248 at the end. And that leaves us with 7 IP addresses. So it's even less IP addresses using classless by changing the subnet mask once again. So this turns classful into classless. So let's take a look at what this means in binary, because then it makes a lot more sense. All right, so there's 10.1.1.1, and you can see what it looks like in binary. Now we take our Class A subnet mask, 255.0.0.0, and you can see on the left-hand side with the binary that we are masking off only the first octet for networks, and the rest of the 3 octets are all being used for hosts. 24 bits for the hosts is 2 to the 24th power, minus 2, of course, for broadcast and the network address. And that shows that we have over 16 million addresses, and most of those are wasted. They're not being used. So then we change over to a Class C type of subnet mask using a Class A address. So we basically just stripped the class out of it. So 10.1.1.1 again, same binary that you see, but the subnet mask, you see, we've moved all of those bits off to the right. So we've filled in 3 octets of bits. So we see 1s going across the first 3 octets with this new subnet mask. So that leaves us with only the 254 addresses on the right-hand side for the host. So we've just saved over 16 million addresses by doing this. 8 bits for the host, 2 to the 8th power, leaves you with 256 host addresses. Minus the 2, of course, for the broadcast and the network. Many IP addresses were saved for other uses. So let's take a public address, and we can say 200.30.1.1, and you can see there that the subnet mask is a 255.225.0.0, what we used to refer to as a Class B. So we can see that there are 65,000 addresses, over 65,000 addresses for both hosts and networks, since we split it right down the middle. But most likely a lot of those 65,000 addresses are just going to be wasted. So if we turn that into what we used to call a Class C subnet mask, 255 3 times .0, then once again we end up saving a lot of addresses because we went down to 254 hosts from 65,000. So let's take this one step further to save even more IP addresses. We have our 200.30.1.1, once again, all nicely laid out in binary, And then instead of a 255 3 times .0 subnet mask, we're going to add a 240 at the end. That means we've reached in 4 bits into the last octet. As you can see in this subnet mask, all the way to the right, we've reached into those first 4 bits. That only leaves us with 4 bits left. So 4 bits for the hosts, 2 to the 4th power. Well, 2 times 2 times 2 times 2 is 16. 16 minus 2 leaves us with 14 hosts. And that saved a lot of IP addresses as well. So you can see how classless IP addressing allows us to stretch out our IP addresses when we need to. We can split large networks into much smaller ones using much less hosts. Going from traditional classful IPs to classless IPs is a great way to save hosts when you need them. I encourage you to create your own examples to get additional practice.